Introduction: the Storage Optimization Challenge. As data volumes explode, storage costs skyrocket, and performance demands increase, database engineers need smarter approaches than just throwing more hardware at the problem. These 6 specialized data structures represent battle-tested solutions that can dramatically reduce storage requirements while maintaining or even improving query performance. Let's dive into each structure and understand when and how to use them effectively. 1. Bloom filter, the probabilistic gatekeeper. What it does, reduces costly lookups by testing whether an element is definitely not in a set. How it works? The Bloom filter uses multiple hash functions to map elements to positions in a bit array. When you want to check if an element exists, hash the element with all functions. Check if all corresponding bit positions are set to 1. If any bit is 0, the element definitely doesn't exist. If all bits are 1, the element might exist, requiring actual lookup. The storage magic. Instead of storing the actual data elements, you're storing just a compact bit array. For millions of records, this might be just a few kilobytes compared to gigabytes of actual data. Real-world applications. Database query optimization. Before hitting disk to search for a record, check the Bloom filter first. Distributed systems. Quickly eliminate nodes that definitely don't contain your data. Web crawling. Avoid recrawling URLs you've already processed. Cache systems. Prevent expensive cache misses for non-existent keys. Trade-offs. False positives possible, says element exists when it doesn't. No false negatives, if it says no, it's definitely no. Cannot delete elements without rebuilding. 2. Hyperlog Hollow, the cardinality counter. What it does, estimates the number of unique elements in massive datasets using minimal memory. The problem it solves, counting unique visitors, unique IP addresses, or distinct values typically requires storing every element you've seen. For billions of elements, this becomes prohibitively expensive. How it works. Hyperlog Hollow uses hash functions and statistical properties of random distributions. Hash each element and look at the binary representation. Count leading zeros in the hash. Use the maximum number of leading zeros seen to estimate total unique elements. The more leading zeros, the more unique elements likely exist. Storage efficiency. Instead of storing billions of actual values, Hyperlog Hollow uses just 1.5 kilobytes to estimate cardinalities up to billions with a plus or minus 2% accuracy. Perfect for analytics dashboards, unique visitors this month, database optimization, estimating distinct values for query planning, real-time metrics, stream processing where exact counts aren't critical, A/B testing, measuring unique user engagement. The trade-off, approximate results, but the accuracy is typically sufficient for business decisions. 3. Cuckoo filter, the deletion-friendly alternative. What it does, like Bloom filter, but supports deletions and uses less space for equivalent false positive rates. The innovation. Traditional Bloom filters can't delete elements because multiple elements map to the same bits. Cuckoo filters solve this by storing fingerprints, or partial hashes, instead of just setting bits. How it works. Uses 2 hash functions to determine 2 possible locations for each element. Stores a fingerprint of the element in one of these locations. If both locations are full, kicks out an existing element, like a cuckoo bird. The kicked out element finds an alternate location. Storage advantages. Better space efficiency than Bloom filters for low false positive rates. Supports deletions without rebuilding, maintains constant lookup time. Use cases. Cache systems, where entries need to be evicted. Database indexes, where records can be deleted. Security applications, blacklists that need updates. Content distribution, managing frequently changing content sets. 4. Minhash, the similarity detective. What it does, estimates similarity between sets efficiently, enabling near-duplicate detection and clustering. The core concept. Instead of comparing entire sets element by element, expensive, Minhash creates compact signatures that preserve similarity relationships. How it works. Apply multiple hash functions to all elements in a set. Keep only the minimum hash value for each function. The resulting signature vector represents the set. Similar sets will have similar signatures. Storage benefits. Compare sets of millions of elements using just small signature vectors. Enable similarity search without storing or comparing full data sets. Scale similarity computations to massive data sets. Practical applications. Duplicate detection, find similar documents, products, or records. Recommendation systems, users that like this also like that. Data deduplication, identify and merge similar database records. Content moderation, detect near duplicate spam or inappropriate content. The signature matrix, the visualization shows how different sets, A, B, C, D, get reduced to compact signature vectors while preserving their similarity relationships. 5. Skip list, the probabilistic search structure. What it does, provides fast search, insertion, and deletion with predictable performance using less memory than traditional balanced trees. The elegant design, skip list builds multiple levels of express lanes over a sorted linked list. Level 0 contains all elements, higher levels contain progressively fewer elements. Search starts at the highest level and drops down when needed. How the levels work. Each element has a random height determining which levels it appears in. Higher levels act as shortcuts for long-distance jumps. Expected search time is O log n like balanced trees, but simpler implementation and often better cache performance. Memory advantages. No need for complex balancing operations like AVL or red-black trees. Predictable memory usage patterns. Better cache locality than pointer-heavy tree structures. Concurrent access is easier to implement. Database applications. Range queries. Efficiently find all records between 2 values. Sorted indexes, maintain sorted order with quick updates, time series data, quick access to data within time ranges, leaderboards, maintain rankings with frequent updates. 6. Countman Sketch, the heavy hitter finder. What it does, tracks frequency of items in data streams using minimal memory, perfect for finding the most common elements. The stream processing challenge. When processing millions of events per second, you can't store counts for every possible item. Countman Sketch solves this with clever approximation. How it works, maintains multiple hash tables, the sketch matrix. Each item gets hashed to one position in each table. Increment counters at all corresponding positions. To query frequency, take the minimum value across all relevant positions. Why min matters. Hash collisions cause overcounting, but taking the minimum across multiple independent hash functions gives the best estimate of the true count. Storage efficiency. Instead of potentially millions of counters, you maintain just a small matrix, maybe 1000 by 10, regardless of how many unique items you see. Perfect applications. Real-time analytics, top trending hashtags right now, network monitoring, detect traffic anomalies and heavy hitters, database query optimization, estimate frequency for join ordering, fraud detection, identify unusual patterns in transaction streams. Resource management, track most frequently accessed files or URLs. The hash functions. The diagram shows how multiple independent hash functions, hash function 1, 2, and 3, map items to different positions, providing redundancy and accuracy. Choosing the right structure. For membership testing, Bloom filter. If no deletions, or cuckoo filter if deletions needed. For cardinality estimation, hyperlog hollow when you need to count unique elements. For similarity analysis, minhash when comparing sets or finding duplicates. For ordered data, skip list when you need fast range queries and updates. For frequency tracking, count min sketch when processing high volume streams. Implementation strategy. Start small. Begin with one structure that addresses your biggest storage pain point. Measure impact. Track storage reduction and performance improvement. Combine strategically. These structures often work together, e.g. Bloom filter plus skip list. Monitor accuracy. Understand the trade-offs between storage savings and precision. The bottom line. These data structures represent decades of research into making databases faster and more storage efficient. They're not theoretical concepts, they're battle-tested solutions used by major tech companies to handle billions of operations daily. The key insight is that perfect accuracy often isn't worth the storage cost. By accepting small amounts of approximation, you can achieve dramatic improvements in both storage efficiency and query performance. Master these structures and you'll have powerful tools for tackling even the most demanding database storage challenges.